So when I was asked to give a talk here at this meeting, I was wondering what to talk about, and so I chose to talk about a proposal for an experiment. I'll tell you more about it. And the reason I chose this is, in some ways, I thought it aligned with the spirit of this meeting, where we're, also remembering Rajaji. And, he was a big supporter and champion of INO, which sadly is, I think has evaporated in the language of Murthy. But I think the idea, I think the support for an underground science laboratory has not evaporated. So we are still quite enthusiastic, and there is... Okay. So the bubble has evaporated. No, so I think in general there is still a lot of support for underground science lab, from scientifically and administratively, and there are many experiments that would be housed in one of these this underground science lab that is being thought about. So the mega science vision documents also talk about the underground science lab. And this proposal for this experiment, it's a neutrino experiment primarily, but based on a new technology that I'll tell you about, would also presumably be housed in this underground science lab where it to come up. Okay, so and it's a futuristic thing. There are lots of things to be done. So it's not a finished piece of work. So you'll have to forgive me if I don't have answers to every single one of your questions. But let's start. So, okay. So, there are many people working on it. I am not talking in any official capacity. It's just that there is no official collaboration, so to say. A lot of people have just organically come together and they are working on this idea. But let me still mention some of the people involved. So whatever I will tell you is based on a science case white paper that was submitted to DAE, and there are several of us who wrote that paper. Names will come up in a second. There is a published paper on the idea where we focused only on supernova neutrino detection using this experiment, and that's the second reference, the JCAP reference that I mentioned here. And there's ongoing work by several people, but at least two well-organized groups. One which is called the DAE Task Force. So that involves people from different institutions of the DAE, with several people, and I'll name them in a bit. And then there's a study group of TIFR, which is a bit more physics and more physics-oriented group, which again, actually, although it says study group of TIFR, it does involve people from outside TIFR as well, and again, I'll name them. So there's a bunch of people. Let's see. Again, this is not a complete list. So this is part of the DAE task force, which involves people from BARC, and then there are people from the Heavy Water Board. Actually, you don't see the ex-CEO of the Heavy Water Board here on this list, who used to be, in fact, the convener of this task force, Dr. Nayak, but he has retired, and then the next person, Dr. Srivastav, is in charge. And then this is the composition of, or at least at some point of time was the composition of the TIFR study group, which, as you can see, involves people from elsewhere as well. Many of you are here. There are many others. Some of the names you will find if you go and look at the report that got generated about 2 years ago at the underground science lab meeting that happened in TIFR. Okay, so there's a whole bunch of people involved. More names will come up as we go on. That should give you a sense that there are people interested in it. That's all I'm saying. Okay, but now back to physics. See, the basic idea is this. Most neutrino detectors are sensitive to only nu E bar. Okay, electron antineutrinos, because of inverse beta decay having the largest cross section. Dune is sensitive to nu E, liquid argon. But in many neutrino observation scenarios, it would be very useful to be sensitive to all neutrino flavors. And the reason is simple. You're often interested in things like oscillations. If you know what your total is, if you can actually measure what your total is, then measuring only a part of it allows you to measure the fraction which is related to survival probability, without any theory input. In the case of solar neutrinos, as we remember, so of course there was a solar model of Bakal, and then you measured, let's say, the charge current signal or something like that, or the electron scattering signal, and you normalized it with the standard solar model, and you could say that, okay, I'm measuring less or more compared to what I'm expecting. But that's not as convincing as measuring the neutral current at snow directly, where you say that, see, I don't care about your theory now. Okay, you care about the theory at the level that, okay, sterile neutrinos are not included in the analysis. But if you grant me that there are only three active neutrinos, then the neutral current measurement tells you the total number of neutrinos, the total flux of neutrinos. And then the charge current tells you only the electron neutrino fraction. Take an appropriate ratio, and you have a theory independent measurement of the survival probability. Okay, that's very nice. So we would like to do things like that. We remember that in the case of snow, that was a very, very important measurement, which in my opinion actually solved the problem. Art MacDonald shared the Nobel Prize for this tremendous feat. So we would like to have something like the snow detector. It's very sad that the snow detector did not work for long. So what's the challenge for a snow-like detector? The problem is that you need both neutrons and protons in your detector in order to do neutral current. Okay, so here, as you're seeing, this is a neutrino. It could be neutrino, anti-neutrino, any flavor, whatever you like, interacts with the deuteron, and it dissociates into a proton and a neutron. And then this neutron can in principle be captured on something else. It could be another deuteron, or it could be a gadolinium, and you could see some final product. Okay, so that's the chain of things that should occur in your detector when there is a neutrino-induced dissociation of the deuteron. Problem is that this deuteron is, first of all, very, very expensive and usually unavailable. So the Canadians got it on a loan from some agency, and then they had to give it back. The snow could not hold on to the heavy water. Even if you do have this, there are a few small, I would say, minor challenges. One of them is that this neutron that gets captured on deuteron produces only a small amount of energy, whereas if you could capture it on something else like gadolinium, that's far more efficient and produces more energy. So you could improve upon that part as well. This was a heavy water-based detector, so basically like Super K, but with heavy water. But that meant that there was a large threshold. So the snow threshold was 5 MeV for most analysis. The proton remains undetected in this detector, and then there's no spectral information, because all you are doing is just basically counting the number of these neutron captures. So you have the deuteron dissociate, you don't see the proton, and the neutron gets captured into something which gives you a little blob of light, and you count. That's all that you were doing at snow. But that means that this proton was never seen. Okay? Can we do, so first of all, we would like to have heavy water, but we would like to do better than snow. Okay, and here is the opportunity. The opportunity is that in India, we have a lot of heavy water. So the Heavy Water Board, which works under the DAE, actually has a lot of heavy water already, because we have all these reactors to take care of. And we won't have to buy this heavy water, hopefully. I mean, DAE can loan this heavy water to one of its, let's say, agencies, and then at some point of time it goes back. And not only can India, the Heavy Water Board, make heavy water, we can make organic compounds with deuterium, in them. And it's not doping. All the hydrogen in the organic compound is just completely deuterium. So they can do that. Okay. So that's a big strength. Now we know, because of our experience with Super K, that gadolinium doping works quite well. Okay, so we could just add some gadolinium to our detector and greatly improve this neutron tagging efficiency. And if we work with a scintillator-based detector instead of a heavy water-based detector, then these problems go away. So the proton immediately gives you scintillation light. The threshold is expected to come down because scintillators have large light output, and because you are seeing lots of photons per charged particle, you can in fact start reconstructing spectra. Okay, so this is the opportunity that one has. So I'll tell you more about the details of the experiment, but before we proceed, let's have kind of a sense of what the final thing should look like. So we are thinking of something like a kiloton or 2 kiloton sized detector. So let's say the active material is something we would, for now call DLS, so deuterated liquid scintillator, although it could be heavy water inside which we dissolve a water soluble scintillator. Now that's also a possibility. We have not decided yet, but either way, let's call it DLS, and this is in a tank, and it's surrounded by PMTs inside, some big stainless steel tank with some veto, let's say water veto here or something, and then this is some cavern, electronics, and people above. So that's the idea. So we would need an underground lab, we would need a cavern, all of that. So there's some work that the task force and the study group have undertaken, where some discussion has gone on about what kind of let's say vessel, what kind of active photo detector we would be looking at, and so on and so forth. So these are fairly standard, like no different from what Snow was doing, let's say. So these things are fairly standard. Yes. You mean a veto, like an active veto? So see, I already talked about a passive water veto here, and then there's rock and everything. But if you're doing it at a lower depth, let's say suppose you want to do it at Vizag, which is at about 100 meters or something, you might want to do plastic scintillators on top and then active veto. But again, depends. Yeah. Okay. So this is, if you forget about everything else, scientifically, if you forget about everything else in this talk, this is the slide that you should remember. Okay, this is the slide worth remembering. So what you see here are 4 possible interactions that can happen with deuterium. Nu and nu bar, what this is saying is that it could be any flavor. It's a neutral current channel, small threshold, and you're getting this neutron and the proton in the final state, and the neutrino or the antineutrino just floats by. And for nu E and the nu E bar, in addition, there are charged current interactions that can occur. So this tells you that you can detect nu E's, nu E bars, nu mu, nu tau, nu mu bar, nu tau bar, all of that in a single detector. Okay, this is not true of any other detector that I am aware of. So that's really cool. Not only that, for any one of these channels, if you see, the neutrino, of course, stays undetected. The outgoing neutrino is not detected. So that we can't do much about that. Every single one of these has one or more charged particles in the final state, which would be detected in the scintillator because we have very low threshold. And not only that, in most of them, except for I think this nu E, there is a neutron in the final state. So you would detect the neutron, tag it using gadolinium. Okay? So you have multiple measurements. You have at least 2 signals for every single interaction. That would reduce background tremendously. So the usual way of thinking about it is that you have some detector, and there's always some background, and things are just clicking constantly. That's your noise. But having 2 detectors, two signals that are separated by some well-known time, let's say some 20 microseconds or something, is like having a heartbeat. So instead of having one click, you see a click, click. And that's a very recognizable signature that cannot be faked by background so easily. So you cut down background tremendously. That's why this is good. Okay. So let's talk about the neutral current part first. So this is what we have in mind. So a neutrino or an antineutrino comes in, hits your deuteron, dissociates it into a proton and the neutron. The proton, because it's charged and in the scintillator, it just immediately dumps all its energy. You can quickly, guess that this proton, very heavy, if you're talking about order 10 MeV energy neutrinos, this is very non-relativistic, the outgoing proton. So Bethe-Bloch energy loss rate would tell you 1 over beta square, that the energy loss rate for this proton is extremely high, order 100 MeV per centimeter. So it basically does not leave a track or anything. It just basically dumps all its energy at the spot almost. You don't see a track. But the neutron, it scatters around. And normally it would actually scatter around for quite a bit, and I will give you an estimate. But our idea is that you put some gadolinium, which has a very large neutron capture cross-section, and then it gets captured rather quickly. And I'll tell you why this is useful to do. So why this is useful to do is that you might be a bit worried about secondary interactions. What happens if this neutron, instead of getting captured or deuteron or whatever, goes and hits another deuteron and dissociates it and sets off a chain reaction? Then the next deuteron breaks, another neutron comes out, which wanders around, hits another deuteron, breaks that, and then your detector starts glowing. You don't want that. So you want the neutron to get captured quickly and not cause further dissociations. So it turns out that's kind of guaranteed. The fine state protons lose energy quickly and travel less than a centimeter, as I just told you. The neutrons undergo the following secondary interactions. It can undergo elastic scattering with whatever nuclei are there. It can be radiatively captured, or it can cause this breakup. And this is a bit dangerous if you don't want your detector to suddenly start glowing. So we computed these things, and what we find is, so x-axis is the kinetic energy of the outgoing neutron, and this is the rate of various interactions. This gray line is the rate of deuterium breakup. Okay, and this red and blue lines are the rates of elastic scattering on deuterium and carbon. So if you start with some 10 MeV outgoing energy, you undergo these elastic scatterings and you go down in kinetic energy like this. Okay. Now, if you did not put the gadolinium, which is this green line, this is the capture on gadolinium cross sections, it was not there, then in order to get degraded, you would have to have many elastic scatterings with the deuteron or the carbon. Okay, and you can compute how many. However, if you put the gadolinium, then it, quickly, degrades its energy by having these elastic scatterings and then gets captured, by the gadolinium. So we can estimate that. And this is the number of elastic scatterings that, about 30 to 35 that you would need in order to get captured. And if there was no gadolinium, this number would be of the order of 3000 instead. So you can then estimate that without gadolinium, this neutron would rattle around for about 20 milliseconds. That's too long. Basically, if you have secondary interactions that occur 20 milliseconds after the primary, you will have overlapping signals and you will get confused. You will not be able to reconstruct the events very well. But with gadolinium, you can reduce this 20 millisecond down to 50 microsecond because 30 instead of 3000. And then it's a true useful heartbeat signal. You don't want your heartbeat to be too long. It should be, just right. And you can tune this by putting gadolinium. Okay. So this is the reason why we put the gadolinium in the detector. Okay, so that's the neutral current. So the neutral current was what? That we have deuterium dissociation because of neutrino and or antineutrino of any flavor, and the proton gives you scintillation light. The neutron rattles but gets captured on gadolinium and gives you another little blob of light.
You're violating the auto gadolinium.
The efficiency of neutron capture is certainly affected by how much gadolinium you put in. The time to capture is statistically affected by the concentration, of course, but you don't have too much control. You could change it, of course, by doing funny things like what Snow did. Like they had this bulb which had, I think salt water. There's salt phase where there were the little bulbs where they put the gadolinium. They did not put it. They put gadolinium at some point, or they put gadolinium right in the third phase. Yeah, in the third phase they put. So you could do funny things like have like a little balloon inside your detector, like sequence of balloons which have the gadolinium and not else. So then the gadolinium capture only happens inside those balloons. So there are tricks that you can play, but we haven't explored that yet. Yeah. Okay. So that is, as I said, so the proton gives you scintillation, the neutron gets captured, and you see light there. And so that's your double signature on neutral currents. Charge currents, you have, of course, this is already in addition to the neutral current. So charge current is going to happen for nu E and nu E bar. It's in addition to the neutral current. And here's the cross section. Funny thing is that, even these cross sections we had to recalculate. So it turned out that for deuterium, like Snow had the cross section, they probably had it internally somewhere, but we wanted also the differential cross sections, as a function of direction and so on. And Bhavesh, who was a postdoc at TIFR at the time, Bhavesh Chauhan, who's now faculty at BITS Pilani, he quite bravely, first of all, confirmed that whatever was available in the literature was basically correct. There were a few typos which we corrected, and recalculated the cross sections using pi-less effective field theory. And these are his results. So what you can see as a function of energy of the neutrino or the antineutrino, the cross sections, and two different techniques. One using something called a phenomenological Lagrangian approach, and the other using a pi-less EFT, and they all more or less agree that it's fine. Okay, so we computed these cross sections, and not only the total cross sections, but the differential cross sections. These are available in the paper and also in this GitHub page that Bhavesh maintains. Okay, now why do you want to do all this other than just the fun and the giggles of building a new experiment? So it's, first of all, it's a new technology, right? So like deuterated scintillator, no one's ever built it at any scale. So that would be nice, but it's not just that you demonstrate some new technology. There is a clear science case for it. One of the important things that you can do, so this is a list of things that you can do, not exhaustive, there are other things. One of the interesting things that you can do is, because you lower your threshold from 5 MeV to 2 MeV, you become sensitive to this region of energy where the solar neutrino survival probability changes from 0.57 to 0.3 or something. I'll show you the plot in a second. And that's the MSW turnover. And so if you can map that out, that would be a much more precise test of MSW physics, which has never been done, and I'll show you more about it in a second. You could become sensitive to the day-night asymmetry of solar neutrinos. There are unique opportunities with supernova neutrinos, and I'll tell you a little bit about it. What I will not tell you here today because of lack of time is that this detector can do everything that a normal scintillator detector does. So dark matter, boosted dark matter, and atmospheric neutrinos at the lower end, and all the things that, for example, Juno will do, this can do. Of course, at a slightly smaller scale. So Juno is 20 kiloton. This would be maybe 2 kilotons, but it can do. Okay, and maybe new ideas as well. So let's quickly talk about some of the scientific things that it can do. So here, this is the neutrino energy in MeV, 0 to 6. Snow threshold was here at 5 MeV. And this is events per kiloton per year, log scale. This is our computed event spectrum. And in this window between 2 to 5 MeV, already you're seeing about 300 events per kiloton per year. Okay. So let's say 1 kiloton detector in 1 year sees about 300 events. Okay. So with 300 events, you can guess what's the typical uncertainty on your survival probability. It's about 5%, 6%. And that's this point here. So here again, energy now in log axis. This is survival probability. This gray band is the theoretical prediction for the survival probability as a function of energy. It goes from 0.57 at the lowest energies to about 0.3 at the highest energies, and that's because of adiabaticity, breaking down at around 2 to 5 MeV. At lower energies, there are measurements, from importantly like Borexino and other detectors. At high energies, there's of course SNO and SK, and these are mostly the 8 boron neutrinos that give you this measurement. But you see, in between this Borexino PEP result, which has large error bars, of course, and the 8 boron result, actually, there is no data here. Okay. There's no data basically between 1 and 7 or 8 MeV. Okay. So this whole space is completely empty, and this red data point doesn't actually exist. So this is what TLS can provide you. Okay. And now if you see, without this data point, actually we haven't really tested the key part of this theoretical prediction. We've seen the two Platos, but we don't actually measure how it turns over. And that would be a much more precise proof of the LMA-MSW solution. And so one can do that. Okay. Of course, you could discover that, something else is happening in that region, and that would be much more exciting, of course. Okay. You could look at the day-night asymmetry. So the sun shines day and night in neutrinos. In fact, at higher neutrino energies, let's say above 10 or 12 MeV, you actually see more neutrinos at night than during the day, I guess. So I forget how this is defined. But in any case, as a function of energy, whether you see more neutrinos in the day or night, that changes. It also changes by latitude and other things. But let's say this is being done here at the latitude somewhere in India. I think Indu produced this plot, so she can tell you more about exactly what assumptions went in. But the point is this, that you focus on this red curve, which goes through this computed points, and you can see that day versus night, it changes sign at about 10 MeV. And because now you have a large detector capable of measuring neutrinos at these MeV energies, you could, track this. Other detectors haven't quite been able to do this, partly because they are never at this, near equator latitude like India. So the most neutrino detectors are above the tropics or below the tropics, and then this effect becomes much smaller there. And this is not a new idea. This is an idea that has existed in our community for 2 decades, at least 2.5 decades. And I believe this this excerpt is from one of the web proceedings from one of the webs that happened here, right? I don't know if this hall was there. Yes, yeah. So this is a pretty historic document. So of course, we don't build a detector just for supernova neutrinos, because we can't guarantee that supernova will happen in our galaxy anytime soon. But we are aware that when stars explode, they emit lots of neutrinos. You're going to see order 10 to the 3, 10 to the 4 neutrinos in about 10 seconds in any kiloton size detector. These things happen about 1 to 3 times per century. The last one actually in our galaxy was around 1900. This was not seen, but the supernova remnant is now being seen. So we know that this was not seen by eye because it was probably dust obscured. Of course, 87A is much more famous. Everyone knows that it happened outside our galaxy in the LMC. So these things happen, not as often as I guess we would like as neutrino physicists, but very important opportunities because they emit all 6 neutrino flavors. So 3 flavors and their anti-neutrinos. And this DLS type detector would be amazing because it would detect every single flavor, And so that would be very interesting. And one of the things that I'm showing here is that because the statistics can be pretty high, you can try to do a measurement of the outgoing proton kinetic energy. So the scintillation light that you see, turns out, of course, that the scintillation light is quenched a little bit because this proton dumps all its energy in about 0.1 mm or whatever, 1 mm this length. So the scintillation gets saturated. So the scintillation light is not equal to the kinetic energy. It's only a fraction. But this is something that you can calibrate in the lab, a priori. And so by measuring how much scintillation you are getting, you can back calculate how much kinetic energy it must have had. So you can do all of that. And if you know this calibration reasonably well, you can actually, then predict, you can in fact reconstruct back the original neutrino average energy from the measurement of the outgoing proton kinetic energy, the quenched outgoing proton kinetic energy, and so on. So you can do these measurements. I'm out of time, so let me quickly wrap up. You can actually measure the spectrum of these events, as I told you, because you now know this differential scattering cross section that we computed, and this is the quenching factor. So this is how you do it. Last couple of slides. So this is all a dream because many things have to yet be done. Most importantly, we have to demonstrate the feasibility of this technology on some scale. And one of the things that that has to be done is, first of all, you have to synthesize this deuterated liquid scintillator. That's already a hard step. So before that, we want to try to see if we can just take heavy water, D2O, and put in and put in water soluble scintillator in it and do some of these things. There is purification aspects, safety issues associated with inflammability of the scintillator, structural engineering issues, several other things. Very quick progress report. So synthesis and testing of the lab scintillator, including its fluors and interfacing with the detectors. This is already being done at VRC by these people. The studies on DLS synthesis by chemists at VRC. There is some low background setup and testing of the purity of the D2O that we have been discussing with Vandana at TIFR. The water-based liquid scintillator, closed loop purification, PMD setup. This is being carried out at Brookhaven National Labs by Milind. There is a detector simulation in GANT, already a preliminary one that's being set up by Deepak at Central University. And there are lots of physics studies happening. Many more people are involved. Our main strengths are that we own the heavy water, as DAE. So we have access to that. That's the main thing. That's the reason that no one else can do it. No one else has access to this heavy water. Geographical location is another thing. That's what allows this day-night asymmetry measurement. And generally, the ecosystem, within the DAE with the BRC and others, it just makes it possible for such an experiment to be built. So I'll skip a few slides, including that how this detector actually compares to other ideas in the market. Basically, it does equally well or better, and that's my summary. Okay.
Any questions?
This is very interesting to hear about this. So one thing I remember from SNO was the levels of the radio purity that are required. So those were very stringent already for snow. Is it even more so now you're trying to lower the threshold, or can you live with the same sort of tolerances that snow had? Not just for the heavy water, but also all the materials that go in, the acrylic, the steel, and everything has to be radio pure.
So we don't. So for quick answers, we don't know because we would need at least a simulation, in GIANT to answer this question quantitatively. And in fact, if we wouldn't start by trying to do this 2 to 5 MeV measurement with slower threshold. I think what we would probably do if this project proceeds in the right way is first we would repeat snow. We would have a threshold of 5 MeV and measure neutrinos above it, and then we would slowly reduce threshold with better purification. I think that's the way we would go. We would probably need help from people who have more experience with purification, like maybe the Boraxino people even, because they have wrapped up. So, yeah, so it's very preliminary. So, I don't know how to do this.
Okay, thank you.
Yeah.
So, thanks for the nice talk. I'm just curious if we know whether gadolinium compounds are heavy water soluble, because that was the problem in Super K. They had to change the thing, right? Compound. So do we?
Yeah.
Because snow did not use gadolinium.
Yeah. So again, the quick answer is we don't know, but my understanding is that the physical chemistry of water and heavy water are not that different. The only difference is essentially that heavy water is like whatever 2 AMUs more, so it diffuses a bit slower. Okay. Other than that, basically there is no difference in chemistry.